Have you ever taken a really difficult math test, sweated over some complex problem, and finally gotten the right answer, only to get the test back and see it marked wrong?
Oh, yeah. The absolute worst feeling.
Right. You look at the margin, and your teacher has written in giant red letters, right answer, but your work makes absolutely no sense.
Because you didn't actually solve the problem. You collided with the correct final number by pure accident.
Exactly. It's that classic show your work dilemma. But today, we're looking at that exact scenario translated into the high stakes world of AI generated code analysis.
Yeah, and it is a wildly fascinating case study. Welcome to today's deep dive, everyone. We are unpacking a slide deck from 2026 by a developer who goes by the handle at Gingers.
And the presentation is titled, Does Order Matter?
Right. So this developer was investigating an AI-generated report. It was a markdown file called ordermatter.-md that made a very bold, very definitive claim about a mathematical algorithm.
Specifically, the parallel Bairstow method. Okay, let's unpack this. The AI claimed, without any caveats, that this Bairstow method is theoretically order independent.
Which is a huge claim.
Right. For anyone prepping for a project involving multi-threaded software, you know that order independent is essentially the holy grail of parallel computing.
It really is. It means you can run an algorithm's various processes in absolutely any sequence. Thread A can finish before thread B, or vice versa, and you are mathematically guaranteed to get the exact same result every single time.
Which is, critical when you want to just throw dozens of processing cores at a massive computational problem.
Exactly, because if the order doesn't matter, you don't have to write complex, bottleneck-inducing code to strictly orchestrate which thread finishes when.
You just let the cores run wild.
Yeah, exactly. But the developer Gingers looked at this AI report and immediately doubted the claim.
And for good reason. I mean, the conclusion sounded plausible, but the AI's proof was built on a completely bizarre foundation.
Yeah, to understand why the developer was so skeptical, we have to look at what the AI actually tested in its proof versus what the Bairstow algorithm actually does under the hood. The discrepancy is, frankly, staggering.
So what did the report actually say?
Well, the AI declared three main things. First, that the order of a process called suppression is irrelevant. Second, that the local math solves are independent of each other. And third, that the outer loop of the code can run in any sequence.
Like processing items 0, 1, 2, or running them backwards 2, 1, 0.
Right, and it claimed you'd get identical results either way.
Okay, so how did the AI prove this massive claim?
Well, this is the crazy part. It proved it by demonstrating that if you multiply polynomials in different orders, the differences in the answers are negligible. Like 10 to the negative 14th power negligible.
Wait, really? The AI simply proved that polynomial multiplication is commutative?
Yep. It mathematically certified that A times B equals B times A.
But wait, that's just proving a basic axiom of algebra. I mean, it's mathematically true, sure, but it has almost nothing to do with the actual software mechanics. The real code doesn't just statically multiply polynomials.
No, it doesn't.
It composes sequential 2x2 linear solves, specifically in a step called suppress old. And these solves actively mutate the remainder in place.
Right, which is a totally different operation.
It's like doing long division on paper. When you process one column, you carry the remainder over to the next column. If you randomly swap the order of the columns you are processing, you're carrying a completely different remainder into the next step. You literally change the underlying numbers you are working with.
What's fascinating here is that the AI completely missed that sequential mutation. It evaluated a simplified imaginary proxy of the code.
Yeah.
We see this frequently with large language models analyzing complex logic. They operate by pattern matching. The AI saw polynomials, it saw mathematical operations, and it just defaulted to proving the commutative properties of polynomial rings.
Entirely ignoring the physical reality of how the algorithm writes and overwrites data in the computer's memory.
Precisely.
I was visualizing this. It's like an automobile assembly line. Each station on that line permanently alters the physical product.
Okay, I like that analogy.
So, Station 1 welds the steel chassis, Station 2 drops in the heavy engine block, Station 3 paints the car red. You can't just randomly swap Station 1 and Station 3.
No, definitely not.
You cannot paint the empty air where a car is supposed to be, and then try to weld a steel chassis over wet paint. Order matters inherently because each step alters the physical reality of the object for the very next step.
Yeah, taking that assembly line analogy a step further, the AI essentially proved that mixing the red paint in bucket A or bucket B yields the same color.
Right. True. but entirely unhelpful.
Exactly. Unhelpful if you're trying to figure out if you can paint the car before you build it.
Right.
Because the AI missed that mutating chain, its proof is completely worthless.
So the developer was back at square one, looking at a worthless proof and still not knowing if the algorithm was actually order independent.
Which meant they had to abandon the AI's proxy altogether and look directly at the fundamental architecture of the algorithms themselves.
And this brings us to a major crossroads in numerical computing. Because when we talk about simultaneous root finding, which is what this code is doing, there are two heavyweight mathematical frameworks.
Right, the Jacobi method and the Gauss-Seidel method.
And we see both variants in the Gingers project. So let's look at the Jacobi variant first, which in the code is called Te-Bairstow even MTT.
So in methods like Aberthurlik or Bairstow, the Jacobi form operates under a very specific constraint. It updates all of its calculations simultaneously from a frozen previous iteration.
A frozen iteration, meaning nothing is changing while it works.
Exactly. Everything it calculates is a pure function of a completely static historical state.
Let's ground this in something visual for you listening. Imagine you are playing a hyper-fast multiplayer video game. The Jacobi method operates like the game server, calculating the graphics for the very next frame. It takes a paused, frozen snapshot of exactly where every player's at, say, millisecond 100.
Right, the total freeze frame.
Yep. It then uses that frozen snapshot to independently calculate where player 1 will be at millisecond 101, where player 2 will be, and so on. Everyone's next move is calculated based on that single, unmoving moment in time.
Contrast that with the Gauss-Seidel variant, which is simply named Te-Bairstow, even in the codebase. Gauss-Seidel completely discards the concept of a frozen snapshot.
It just ignores it.
Yeah. Instead, it pulls in freshly updated data the literal microsecond it becomes available. So back to your video game analogy, Gauss-Seidel is trying to calculate player 2's collision physics, while player 1's updated position is bleeding into the calculation midstream.
Oh, wow.
Yeah. Player 1 moves, and instantly, player 2's mathematical reality shifts before player 2 is even finished calculating their own move.
Wait, so you were constantly pulling in live, mutating data to do your math? That sounds incredibly volatile.
It is volatile, but it raises a profound point about determinism in parallel computing. If you perform complex arithmetic on a frozen state, like the Jacobi method does, you mathematically guarantee that the operations are commutative.
Because the inputs aren't changing under your feet while you work.
Exactly. Therefore, the Jacobi method should theoretically be perfectly order independent. But Gauss-Seidel relies on that live data flow. If player 1's thread processes a microsecond before player 2's thread, the mathematical outcome is totally different than if player 2 processes first.
So it is inherently order dependent by design.
Exactly.
But, theory is great, but in computer science, theoretical determinism isn't enough. You have to compile the code.
They have to actually run it.
Right. You have to force silicon processors to crunch the numbers and see what actually happens. So the developer built a rigorous experimental framework.
Yeah, they created a Python mirror of the exact Rust arithmetic to run side-by-side comparisons.
And for the test subject, they used a degree 8 palindromic polynomial with the coefficients 10, 34, 75, 94, 150, 94, 75, 34, 10.
And I just want to point out, a palindromic polynomial is a brilliant choice for a stress test here.
Why is that?
Because the coefficients mirror each other perfectly from the center out, so the math creates this beautifully symmetrical landscape. If a non-deterministic processing error introduces even the slightest asymmetry into the root finding process,
it'll stick out like a sore thumb.
Exactly. It will become glaringly obvious against that balanced background. So the developer ran 6 distinct stress tests on this polynomial.
Okay, let's start with the micro level that suppress old order we talked about earlier. These were experiments 1 and 2. The developer first tested this using exact rational arithmetic in Python.
Meaning no decimals, no rounded numbers, just pure fractions.
Right. They tested all 24 possible permutations of the suppression order, and the outcome was actually shocking.
The suppression composition actually is exactly commutative in pure math.
Wait, so the AI's conclusion was right?
Yes, but again, for the entirely wrong reason.
Wow.
It got the right answer, but the work on the test was total gibberish. The AI said the code was order independent because it thought the code was just multiplying polynomials.
Right.
But the developer proved it was commutative even when performing the complex sequential linear solves.
Yeah.
Because dividing by the product of factors in exact math happens to naturally resolve into an order-independent operation.
That's incredible luck on the AI's part. But actual computers running in server farms don't use pure exact fractions. They use floating point numbers.
Yeah, they have to represent decimals in binary code. And because binary can't perfectly represent a number like zero point 0.1, the computer has to round it off.
And these microscopic rounding errors compound rapidly. So the developer moved to a second test, running the exact same operation using 64-bit floating point arithmetic. Does the order matter when the processor starts rounding off messy decimals?
Barely. The maximum difference across all 24 different processing orders was 1.0, 7 times 10 to the negative 14th.
Which is tiny.
It's microscopic. That number is known as machine epsilon. It represents the absolute smallest difference the computer's underlying physical architecture can even register. The developer even pushed a system with near singular matrices to intentionally break the math.
Wait, what exactly does a near singular matrix do to a processor?
So imagine two roots, two solutions to our polynomial that are incredibly close together. When the algorithm tries to resolve them, it ends up having to divide by numbers that are practically zero.
Okay.
In floating point arithmetic, dividing by near zero forces the computer to wildly overcompensate, which massively amplifies those tiny rounding errors we just talked about.
So it's a stress test.
It is the ultimate stress test for numerical stability. Yet, even under these brutal conditions, the differences in output stayed at practically zero. At the micro level, the suppression order truly doesn't matter.
So the individual components are safe. But the real question is how the entire algorithm behaves when swept across multiple processing threads.
Right, the macro level.
So the developers set up a showdown between the frozen state and the live state. First up was testing the Jacobi processing order experiment 3. They ran the jobs in sequence 0, 1, 2, 3, then reversed it to 3, 2, 1, 0, and then shuffled it randomly.
And the results perfectly validated the theory. Changing the processing order yielded bit-for-bit identical results.
Bit for bit identical.
Not just close, not just machine epsilon close, but exactly equal down to the literal microscopic zeros and ones stored in the computer's memory.
That's amazing.
Because every job was calculated as a pure function of that frozen historical snapshot, the order of execution was entirely irrelevant to the outcome.
the absolute triumph of the frozen state.
Truly.
Then they tested the Gauss-Seidel sweep experiment 4, the live array method. Processing the jobs in reverse order yielded total chaos.
Oh yeah. We aren't talking about 10 to the negative 14th anymore. The difference was roughly 9.8.
9.8. That is a catastrophic structural change in the output simply because the threads read the data in a different sequence.
A difference of 9.8 in a root-finding algorithm means the data mutations cascaded. The early calculations mutated the live state, which sent the subsequent calculations down an entirely different, highly divergent mathematical path.
Proving definitively that Gauss-Seidel is dangerously order-dependent.
Exactly.
And you see this cascade play out in convergence speed as well. That was experiment 5. When they tested the Jacobi method with permuted initial guesses, it took the exact same number of iterations to solve the polynomial every single time, predictable and stable.
But the Gauss-Seidel method varied wildly, taking anywhere from 6 to 10 iterations to finally converge on the answer, all depending on the thread order. It eventually found the roots, but the computational path it took was entirely unpredictable.
Here's where it gets really interesting. After proving all of this, the developer went back and ran one final test experiment 6, rerunning the AI's original polynomial multiplication experiment.
Ah, yes.
And the difference was exactly 0.
Because it was completely trivial. The developer proved that the AI had essentially performed a mathematical parlor trick that distracted from the mechanical reality of the software.
Yeah. So tallying up the final verdict from the data is eye-opening. The parallel Jacobi method, the MT variant, is perfectly order-independent. You can parallelize those threads across 100 CPU cores and you are golden.
But the single-threaded Gauss-Seidel variant is the exact opposite, which reveals something pretty wild about the code base itself.
What's that?
The function Peerstow even is actually misnamed. Because it operates natively as a Gauss-Seidel method, calling it a parallel method is incredibly misleading.
Because trying to run it in parallel would introduce massive data races and silent bugs.
Right. A simple naming convention can completely obscure the mathematical reality happening inside the CPU.
So what does this all mean for how we use AI to analyze our work? I mean, we solved the mystery, and we proved the AI arrived at the right answer through complete hallucination of the logic. But stepping back, why does this granular detail about polynomial root finding matter to you, listening to this, in the broader landscape of technology?
Well, this isn't just an eccentric quirk of the Rust programming language. The developer noted these findings apply universally across sibling projects.
Right.
There's a Python version called Ginger that uses a thread cool executor versus a single-threaded loop, and a C++ version called Gingerclap with root finding MT versus a bare stow even stop.
Because the programming language is just the syntax. Order independence is a property of the fundamental algorithm structure. Whether you build a bridge out of steel or reinforced concrete, the laws of physics apply equally to both.
Absolutely. The underlying behavior we are desperately trying to secure here is determinism.
And determinism ensures that providing the same input yields the exact same output bit for bit every single time you press run.
Which is foundational for two massive reasons in modern engineering. The first is reproducible research.
Okay, unpack that for us.
Say you are using parallel computing to model aerodynamic fluid dynamics or protein folding in pharmaceuticals. A scientist in another country needs to be able to compile your code and get your exact data.
Right.
If your algorithm is secretly order dependent based on how their specific CPU dynamically schedules threads, their results will silently drift from yours. And the scientific method completely breaks down.
That's terrifying. And the second reason hits closer to home for any software engineer: debugging in continuous integration, or CI pipeline.
Oh man, CI pipelines are automated server environments where newly written code is constantly compiled and tested. If you use an order-dependent parallel algorithm, you will inevitably spawn Heisenbugs.
Heisenbugs, I love that term.
It's perfect, right? These are bugs that randomly appear and disappear based on the load of the server. On Tuesday, thread A might finish a millisecond faster than thread B, and the code passes.
But on Wednesday?
On Wednesday, the server is under heavier load, thread B finishes first, the live data mutates differently, and the entire test suite fails.
And because it's non-deterministic, when the developer tries to recreate the bug on their local laptop to fix it, the bug just vanishes.
Exactly. You cannot debug an error that refuses to reproduce. By proving that the Jacobi method is bit-for-bit order independent, the developer completely eliminated an entire class of impossible-to-reproduce Heisenbugs from their software ecosystem.
If we connect this to the bigger picture, this investigation also establishes a critical rule for the modern engineering era: trust, but verify, especially regarding artificial intelligence.
Yes. The danger in this story wasn't that the AI was lying. The danger was that the AI handed over a mathematically sound proof built on an entirely irrelevant foundation.
Yeah.
We have to ensure our tools are testing the messy, mutating reality of the system, not just some simplified proxy that makes the math look elegant.
So let's summarize the golden rule established by this 2026 source material. It boils down to a very concise premise. Frozen state means order free. Live state means order matters.
Perfect summary. Both the Jacobi and Gauss-Seidel variants are deterministic in their own controlled environments, but they behave vastly differently the second you introduce parallel multi-threading.
The frozen state of Jacobi provides a mathematical safety net. The live state of Gauss-Seidel demands strict sequential respect.
Because knowing which underlying mathematical reality you're actually working with, regardless of what a function name implies, or what a highly confident AI report tells you, is literally the difference between writing rock-solid software and introducing catastrophic data corruption.
Which leaves us with a truly unsettling final thought for you to ponder. We caught this specific AI hallucination because a highly skilled developer took the time to meticulously audit the math.
Yeah, thankfully.
But consider the current trajectory of technology, where AI is increasingly being used to generate, review, and certify massive code bases for high-stakes environments, like autonomous vehicles or medical hardware.
Right.
If an AI writes a multi-threaded parallel process for a self-driving car's sensor array and incorrectly certifies that it's order independent based on a flawed, irrelevant proof, what happens when that car is on the highway?
A non-deterministic bug in a real-world environment.
Exactly. The threads process in a slightly different order due to a random CPU spike, the live state mutates improperly, the sensor data diverges, and the car makes a catastrophic error.
Wow.
But here is the truly terrifying part. Because the failure was caused by a non-deterministic Heisenbug, the crash is mathematically impossible to reproduce.
Because the environment changed.
Right. When investigators pull the logs and rerun the exact same inputs in a courtroom or a lab, the threads will likely schedule differently, and the software will perform flawlessly.
So how do you even prove it happened?
How do we assign legal liability to an AI-generated bug that physically ceases to exist the moment you try to audit it? Just something to keep you up at night the next time an AI assures you that your code is mathematically sound.